In this tutorial, we are going to go over radioactive half-life, specifically what it is, how you measure it, and how you can make half-life calculations. So we've been talking a lot about radioactive decay and how some elements, their nuclei are unstable and they will decay over time into something else. So half-life is the amount of time it takes for that to happen. So let's say I have a little pile of, say, carbon-14, and it weighs, I don't know, 10 grams. Half-life is defined as the amount of time it takes for half of a radioactive sample to decay. So carbon-14, if I have 10 grams of carbon-14 and I let it decay over time into its daughter element, which is nitrogen-14, by the way, in case you're wondering. So when we have, say, 5 grams of nitrogen-14, which is what it decays into, and then 5 grams of carbon-14, the amount of time it took for our 10 grams of carbon to break in half, or for half of it to decay, is called half-life. And every element has a half-life. Every radioactive element has a half-life. For carbon-14, that amount of time is 5,730 years. So if I have 10 grams of carbon-14, it would take 5,730 years for half of it to decay into nitrogen-14. And then if we wait another 5,730 years, then we're going to end up with half of our 5 grams, so we'll end up with 2.5 grams of carbon-14, and then the remainder, which would be 7.5 grams of our sample, would be nitrogen-14. So, you know, we have this law of conservation of mass taking place, where we started out with 10 grams and we still have a total of 10 grams of product. It's just that half of it is now nitrogen-14 and half is carbon-14. And then after another half-life, it still adds up to 10 grams, right, total. But we're only left with 2.5 grams of carbon-14 and the rest of it is turned into nitrogen-14. So the amount of time it takes for a sample to decay by half is half-life. So I actually have a graph for the nuclear decay of carbon-14 over time. So in this graph, you know, it's the same numbers I just used here. So here we have 10 grams of carbon-14, and then of course after 5,730 years, we have 5 grams, and then after another 5,730 years, which is a second half-life, we would only have 2.5 grams. And then, of course, after a third half-life, we would have half of 2.5. So if we did another half-life down here, we would end up with 1.25 grams of carbon-14. And then the remainder, of course, would be all nitrogen-14, because that's what it's decaying into, and that would be 8.75 grams. So that's half-life. Every radioactive element has a half-life, so an amount of time that it would require to break it down or decay it by half. So here I have a couple of different elements listed. I've got uranium-238, carbon-14, bismuth-210, and polonium-214, just to give you some examples of the varying degrees of half-life. So we just talked about carbon having a half-life of 5,730 years, as opposed to something like bismuth, which only takes 5 days to break down by half. And then, of course, you have something even crazier like uranium-238, which takes 4.5 times 10 to the 9th years. That's like billions of years. That's a crazy amount of time. So the point being that there isn't a set half-life for all elements, but all elements have a half-life that's unique to that particular radioactive isotope. Okay, so let's talk a little bit how we measure half-life. So half-life is actually measured in a lab. So they take a sample of some radioactive isotope, so maybe like 100 grams of that isotope, And they actually analyze it over time. And they look at how much breaks down over a certain amount of time, and then from that they can figure out the half-life. So they get a little graph, right? So here's a bar graph that shows you the number of half-lives for some element, breaking down from 100 grams to then half, right? And how much time did it take for the 100 grams to go to 50 grams, and they measure that amount of time, and that's a half-life. And then they do another half-life. They wait for it to break down to 25 grams and measure the amount of time, and that would be a second half-life. And of course, after a few half-lives, they'll take an average to get an average half-life. So let's do an example. Here I have the decay of iodine 131. And here's the graph that was made after it decayed for 40 days. So we started out with a 100-gram sample. So we started with 100 grams of iodine 131. And we want to know its half-life. So in order to determine the half-life of iodine 131, we have to figure out how long it would take for it to decay in half, or by half, to 50 grams. So 50 grams is going to be like here, and we follow it over to the graph, boop, and then we follow it down, and we look at how much time that took. And we notice that it took 8 days. So that means that the half-life of iodine 131 is 8 days. So if I were looking at the half-life, which we call, by the way, T1/2, that's how you abbreviate that, of iodine 131 is equal to 8 days. So how much iodine 131 do I have left after 8 days? 50 grams. So the beauty of this is I can actually use this graph to figure out how much of a sample I have after a certain number of days. And so if I want to know how much iodine I have left after, say, 24-ish days, right? Or sorry, 20 days. So this would be about 20 days. Then I can just follow up to the graph and over, and I will see that I have about a little less than 20 grams. So after 20 days, I have a little bit less than, so approximately 18 grams of iodine 131 remaining. So half-life graphs are extremely important to be able to read and to be able to get information from. Or I can do it reverse, right, or opposite of that. I can say, okay, after, like, how long did it take for, say, that's not a very dark color, 30%. So how long for 30 grams of your iodine 131 to be left over? How long would that take for 30 grams to be remaining? So I can find where 30 grams would be on the graph, and I can follow it over and then down and get an approximate amount of time. So probably like 14-ish days. So if you're given a graph, it's pretty easy to read half-life off the graph. There's a little estimating, of course, but there you go. Okay, so let's talk about how we would actually make some half-life calculations. In order to do that, if you remember up here, I gave you this little graph. So I'm going to use the information from this graph to do some half-life calculations that you might see on homework in class. So the first example that I'm going to give you is this question. How long would it take for a 32-gram sample of bismuth 210 to decay to 2 grams? Now, don't make this hard because, it's actually a pretty simple question. You just have to think through what you're doing. So we know that we have 32 grams of bismuth 210 and that it is going to decay by half, so to 16 grams in 5 days. So one half-life, right, 5 days. And then after another 5 days, it is going to decay to half of 16, which would be 8 grams. And that after another 5 days, it will decay to 4 grams. And then after yet another 5 days, it will decay to 2 grams. So it took 1, 2, 3, 4 half-lives. So it took 4 half-lives to do so, and each half-life is 5 days. So you can either just add up 5, 5, 5, and 5, or you can just take 4 times 5, and you will get 20 days. That's how long it took for my bismuth 210 sample to decay to 2 grams. Another kind of question I might ask is something like this. How long would it take for a sample of polonium-214 to decay to 25%? So we know that the half-life of polonium-214 is 1.6 times 10 to the negative 4 seconds. And we're asking how long it would take for it to decay to 25%. So we're assuming we have some sample of polonium-214, and that after 1 half-life, half of it will be decayed to some other substance, right? So here's the other substance it's decaying to. So we had 100%. Now we only have 50% polonium. And then after a second half-life, we would only have 25% polonium left over. So right here, we would have 25% polonium and 75% of whatever it's decaying into. So how long did it take for it to go from 100% to 25%? Well, it took 2 half-lives, right? 1 half-life, 2 half-lives. So it took 2 half-lives for it to go from 100 to 25%, and we know that each half-life is 1.6 times 10 to the negative 4 seconds. So we can either add 1.6 times 10 to the negative 4 to another 1.6 times 10 to the negative 4, or you can just take 1.6 times 10 to the negative 4 seconds and multiply by 2, and you come up with 3.2 times 10 to the negative 4 seconds. So that's how long it took for our sample of polonium to decay to 25%. Okay, so that is my little presentation on radioactive half-life.